Hi everyone. In this video, we are going to have 5 learning objectives. First, we look at what is a prime number, what is a composite number. And also we learn how to do prime factorization. And also we are going to cover how to factor a set of numbers to get the greatest common factor. Also, we want to find how to do greatest common factor given a set of monomials. Okay, let's do this one by one. First, how to determine if a given number is a prime number or a composite number or neither. We need to have the definition first. What is a prime number? Basically, it is a natural number. Natural number are those whole numbers starting with 1, right? 1, 2, 3, 4, 5, and so on. And they are called natural numbers. So a prime number is a natural number that has exactly 2 factors, 1 and the number itself. In other words, prime number can only be divided by 1 and itself evenly. No other number can divide into the given number other than 1 and itself. So some of the, I take that back. So this is the question, are these numbers listed here are prime numbers? Are they prime numbers? So let's look at them one by one. First number is 1. We determine whether a given number is prime number or not by the definition. It has to be a natural number that can be divided by 1 and itself evenly. Only 1 and itself, 2 different numbers. So 1 can only be divided by 1 and 1. So it's not 2 different numbers. So by the definition, this one is not. It's not a prime number. How about the others? Let's do this one by one. 2. 2 can be divided by 1 and 2, and that's the only factor that can divide 2 evenly. So this one is yes. And the third one, 3, just like 2, it can only be divided by 1 and 3 evenly. So this one also, yes, it is a prime number. So last one, 4, apparently in addition to 1 and 4, this number can be divided by 2. In other words, it's not exactly 2 different factors. It has something other than 1 and itself into it. So this one is a composite number. Since they ask us whether they are prime numbers, the answer is no. It's not a prime number. Here are a list of some prime numbers. So if you look at all of these numbers, any one of these, there's many, many more, countless actually. Each one of these can only be divided by 1 and itself evenly. That's why they are called prime numbers. Now, what are the composite numbers? Composite numbers are those natural numbers that can be divided by some other numbers other than 1 and itself. So let's look at the definition on this next page. A composite number is a natural number that has factors other than 1 and itself. Say, in addition to 1 and itself, this given number can be divided by something else evenly. So these are some examples of composite numbers. So let's take 2 of these. Example 10. So in addition to 1 and 10, it can be divided by 2, right? It can also be divided by 5. But as long as we have at least another number that can divide into this given number other than 1 and itself, it is a composite number. Say, let's do maybe another one, say 24. In addition to 1 and 24, it can be divided by 2. 4, 6, 12, right? So it's a composite number. Now, here is an interesting question. That's why I put a star in front of it. It's a little bit special, this number. So is 1 considered a composite number? The answer is no. So we already know from the previous slides that 1 is not prime number because prime number requires to have 2 different factors, 1 and itself. And there's no 2 different factors, just 1 and 1. So it's not prime number. Is it a composite number? No, because in addition to 1 itself, it has to be divisible by something else. So this answer is also no. As a result, 1 is really special. It is not a prime number. It is not a composite number either. Okay. Now, here's a question. How to determine if a given number is a composite number? Now, let's do that using an example. So is 91 a composite number? Let me mention this actually. Any composite number, by definition, can be divided by something other than 1 and itself, right? Actually, any composite number can be factored into prime number factors only. That means any composite number can be written as the product of several prime numbers. They are all prime numbers. In other words, if you have a composite number, it will be divisible by a prime number other than 1 and itself. It will be divided by another prime number other than 1 and itself. So what's the indication? This is just tell us how to determine if a given number is prime number or not. We do that by dividing this number by prime numbers only, because if it's composite number, it will be divisible by a prime number and 1 and itself. So let's try it. We don't need to try 1 and itself, right? We start with next prime number, which is 2. This one is not divisible by 2, because we already learned that only even numbers can be divided by 2. This is not even number, so 2 is out. So it cannot be divided by 2. Next prime number is 3. So we already learned divisibility test of the rules for a number divisible by 3, which is the sum, if the sum of these digits in the given number can be divided by 3, then the number itself can be divided by 3. 1 plus 9, the sum is 10, and 10 it cannot be divided by 3. So 91 can be divided by 3. Next prime number, 5. This one is easy to do. We know only those numbers ending with either 0 or 5 can be divided by 5, right? So this one cannot be divided by 5. Next prime number is 7. And if we try 7, 91 divided by 7, this is 1 7 in 9. Remainder is 2, put on another digit, 3 times 7 equals 21, divided evenly. So 91 can be divided by 7. This is a factor other than 1 and itself. So by the definition, 91 is a composite number. So the answer is yes, it is a composite number. So basically just divide by all of those prime numbers. Okay, let's try another one. The reason I have this second example is that if you think about this possible scenario, when you have a bigger number, when are you going to stop? For example, 3-digit, 4-digit, or even 5-digit number. When are you going to stop testing it, right? So let's try next example. First, 2 is not, because it's not even number. Let's try 3. Add them together, this is 10. 10 cannot be divided by 3, so 3 is not a factor. cannot be divided by 3. Next prime number is 5. Apparently, this one cannot be divided by 5 because the ending digit is not 0 or 5. Next one is 7. Let's try using calculator, so we don't have spend time to do repeating division. Everybody knows how to do a long division, right? So 127 divided by 7, not decimal. So that's not divisible by 7. Next prime number is 11. So 9 is not prime number because 9 can be divided by 3. So 127 divided by 11. You get another decimal number. So 11 is not cannot be divided by 11. Next prime number is 13. So 127 divided by 13. We get 9 point something. So this one is not answer either. Actually, this is where we want to stop. The reason is very simple. If you look at the answer, it's already smaller than your divisor. The prime number, the latest prime number we tried. That means if you try other prime numbers, the number can only get smaller. Remember, I mentioned that all of the composite numbers can be written as the product of all prime numbers only. So in other words, if there is a prime number that can divide into this given number, the result will be another prime number. And because they're all divisible by prime number. And the more important part is not the result is prime number or not, actually, is whether it's smaller than this number or not. If it's getting smaller, and you already try all of the possible prime numbers already. You already try all of those prime numbers already. Okay, that's where we stop. Since all of these are not a factor, so this 127 is a prime number. So I take that back when I said the prime number, if this is a composite number divided by a prime number, and you get another prime number, and that's not necessarily true. Okay, let's move on to the next one. This is the summary how to perform this division to determine if a given number is a prime number or composite number. And take a look at it. And there's a little bit more on the next page. Okay, this last part just tells us when to stop, basically. And by the way, if you're not sure what are those prime numbers that, to use to do division, you can just do all of the whole number starting from say 2, 3, 4, 5, 6. You don't need to worry about whether they're prime or not, as long as you cannot divide into that number evenly, and once your quotient is smaller than the divisor you use to do division, you stop. That means it's prime number. If you still cannot find a number that divided into the given number. Okay, example 1, determine whether 157 is prime or composite. So I just do division. Starting from 2. 2 is not, because this is an even number, and 3. Add the digits together, this is 13. 13 cannot be divided by 3, so we skip that. 5 cannot be divided by 5, 7. Let's try 7. 157 divided by 7 is 2, 14. And 7 cannot be divided by 7 evenly. So 7 is not divisor. And next one is 11. 157 cannot be divided by even directly. Let's try that. 157 divided by 11. So we got a decimal number. So next one is 13. So 13 divided by 13 divided by 157 divided by 13 equals 12 point something. So this is not answer either. But our quotient 12 point something is more than that. So we don't have any number that can divide to 157 other than 1 and this number itself. So this is a prime number. The answer is that 157 is a prime number. Now, this is your first exercise questions. And all of the answers to the exercise questions are in the comment area below the video. You can also make a comment, ask questions. Next topic is that we want to find the prime factorization of a given number. In other words, we want to factor a given number, which is a composite number, into prime factors only. What does that mean? I'll give you a quick example. 20 can be factored into 4 times 5, right? These two are called factors of 20, but they're not prime factorization because 4 is not a prime number. Instead, if you write this as 20 equals 2 times 2 times 5, and these are called prime factorization because all of the factors are prime numbers. So that's our goal for this topic. Okay, a prime factorization is a product written with prime factors only. So let's do this example too. I'm going to do it twice. First, this 84 basically is called a tree method, so-called tree method, because the layout is like a tree. It has branches. Now, since we are doing prime factorization, I'm going to divide this number using prime numbers only. So the first prime number is 2. Apparently, 84 can be divided by 2. So you're going to get 8 divided by 2, that's 4. 4 divided by 2, that's 2. Right? You divide by a prime number on one branch and put the quotient on the other branch. Now keep doing this. This can be divided by 2 again, and we get 21. See the prime number. 21 can be divided by 3. So using all of the prime numbers, try all of the prime numbers. And you got 7. Now 7 is a prime number. That's one way stop. So all of these numbers that you use to as divisors, they are prime numbers. This is called prime factorization. But you don't want to leave your answer like this, all of these numbers on the tree. You want to write the result. This number 84 can be factored into these 4 factors, but the requirement is that we want to write the answer in exponential form. So we have two tools, 1, 3, 1, 7. Remember, factors as products are the product of all these numbers. So write this multiplication and dots. Now, second way to do that is this. I still start with this original numbers. I'm still using tree method. Now, there's a theory which is true that a given composite number can be factored into a unique set of prime numbers. That means this answer we have here is unique. So the indication is that regardless of the process, how you factor it, as long as you do your calculation correctly, you will get the same answer. In other words, you don't have to use the 2 first. You can divide this 84 any way you want. As long as you do division correctly, you will end up with exactly the same answer. So let's try that. This time I say this number can be divided by 4. So I divide by 4, A divided by 4 is 2. 4 divided by 4 is 1. And 4 can be split into 2 and 2. And 21 is 3 and 7. Now I get the same answer. See that? 2 2s, 1 3, 1 7. 2 2s, 1 3, 1 7. Sometimes this can go faster than that, because if you divide by a little bit bigger number, you get a smaller quotient. So let's try another example question. This is A. Now we have a B, big number. So imagine if you use a tool first, and you divide many tools before you can reduce this number to a relative smaller number. But if you use a second approach, we know in the whole number, each trailing 0 represents 10 actually. So 2 0 really means 100. So this really means 3,500, even though we read it as 3,500. We know it is true that we can read it as 3,500, right? This is 100. So 35 and 100. Divided by 35, we get 100. 35 is 5 and 7. 100 just 2 tenths. Like I said a moment ago, you can divide this number any way you want. As long as your calculation is right, the final answer will be correct, because the final answer is a unique answer. This is 2 and 5, another 2 and 5. Now they are all prime numbers. Now let's write the final result in the exponential form. How many tools? We have 2 tools. How many 5s? 1, 2, 3, 3 5s. And how many 7s? We only have 1 7. So how many in total? Just double check. 1, 2, 3, 4, 5, 6. This is 5, another one, 6 numbers. So we don't miss any number. Okay, this is your second set of exercise questions. Now, next topic, how to find all factors of a given number, not just the prime factors, all of those factors. Factors are also divisors. So basically, we want to find out what numbers can divide into a given number. Now, the example we have here is that we want to list all of the factors of 24. How do we do that? We divide by the natural numbers 1, 2, 3, 4, and so on, until the factors repeat themselves. Let's look at what this means. What this means by just actually doing the division. So we divide this given number by 1, 2, 3, 3, 4, 5, and so on, one by one. Okay. We divide 24 by 1. You can use a calculator once the number gets a little bit bigger. You divide by 1, you get 24. So 1 times 24 is 24, right? These two are factors. Now, next number to divide by is 2. Divided by 2, you get 12. So both are factors, because when they multiply together, equal to 24. So both are factors. Divided by 3, we get 8. Everybody knows multiplication table, right? 24 divided by 3 is 8. Divided by 4, we get 6. Right? Now you cannot divide by 5. So next one is 6. What do we get when we divide by 6? We get 4, right? Are these two factors repeating? Yeah, that's same two factors. So that's when you stop. When you stop. Because next one, dividing into that is going to be 8. 8 and 3, they all repeat. So once you have a pair of factors repeat, you stop. That's your final answer. So answer is this. We need to list all of these factors. So I'm going to list it from the smallest to the greatest. So 1, 2, 3, 4, 1, 2, 3, 4, 6, 8, 12, 24. These are the all factors of 24. That means 24 can be divided by all of this, each one of this evenly. So that's called all of the factors. your third set of questions exercise. And let's look at our next topic. Find the greatest common factor of a given set of numbers. So you're given a list of numbers, find the greatest common factor. That means all of your given numbers can be divided by this number evenly, and this number is the largest number possible that can do that. Okay, definition, what is the greatest common factor? Greatest common factor. In some books, they also use GCD, which means greatest common divisor, because factors are divisors. For example, 20 can be written as 4 and 5. So 4 and 5 are factors, right? But they are also divisors. 20 can be divided by 4 evenly, 20 can be divided by 5 evenly. That's why they also call this greatest common factor, greatest common divisor. They are the same thing. Now, by definition, it says it is the greatest number that can divide divide all given numbers with no remainder. That can divide all of the given numbers evenly. Now, how do we actually find the greatest common factor? Let's use 2 examples to illustrate this process. First, let's find the greatest common factor of 24 and 60. And I have 2 methods to show you how to do that. You don't need to do both of these methods. You just need to make sure you know at least one method to be able to do this factoring. Now, the first method is that you want to find the prime factorization of each number. And then after we can easily find out the greatest common factor of the given numbers. Let's show the process. First, I'm going to do the prime factorization of these 2 numbers. This is 4 and 6. 4 is 2 and 2. This is 2 and 3. Now I'm going to write this as the exponential form. We have 3 2s and 1 3. This is the prime factorization. Now we do this, we just repeat this process using 60. This is 6 and 10. 6 is 2 and 3, and 10 is 2 and 5. So right answer is exponential form, 2 2s and 1 3, 1 5. All of the numbers are factors. Now, our greatest common factor, first they have to be common. 2 is common, both true, but how many 2s are common? You look at the smaller exponent. This is smaller. 2 2s are common. Everybody has 2 2s, but not everybody has 3 2s, right? That's why 2 2s are common. So you look at the exponent, pick the smallest one if you have more than 2 numbers to work with. Okay. Now next one, 3. This one has 1 3. This one has 1 3. So 3 is common. Is 5 common? No. The first number doesn't have 5. So this is our final answer, and multiply them out. This is the 4. 4 times 3 is 12. Is that true that 24 can be divided by 12 evenly, and 60 can be divided by 12 evenly? The answer is 5. I almost said 5. Yeah, 60 divided by 12 is 5. So it can divide into both numbers. And 12 is the largest number that can do that. That's why we call it greatest common divisor, greatest common factor. Now, I'm going to redo this problem using another method, which I call it box division. I don't know if there's such a name. Maybe I just invented a name for this. It goes like this. Again, we're still doing greatest common factor of 24 and 60. Okay. So this method is that you put these numbers, we only have 2 in this case, inside this box. Then you try a divisor that can divide into both of this. It doesn't matter this is a composite number or prime number, as long as it can divide both these 2 numbers evenly. So I can try 4, you can try 2, either way, as long as divide into both evenly, that's totally fine. If I use a 4, This is going to be 6. 24 divided by 4 is 6. 60 divided by 4 is 15. Again, if you don't say 4, you do 2. You just need to do another 2 later on down the road. Now, for this 2, repeat the process. I say this 2 can both divide by 3. Divided by 3. I get 2, I get 5. Now, no other number can divide into these 2 numbers at the same time, except 1. But 1 doesn't make any difference because we are going to multiply these divisors together. If you have 1, doesn't make any difference. So we stop here because we don't have common divisor that can divide into both numbers evenly. So our greatest common factor is 4 times 3, and that's 12. So we get exactly the same answer, right? Okay. Let's move on. Another example, this time we have 3 numbers. Again, I'm going to demonstrate this process once again using both methods. First, let's do prime factorization on each of these 3 numbers. And this is 8 and 8. Each 8 actually is a 2, 2, 2, 3 2s, 2 times 2 times 2. If we don't say that, do 2, 4, and the 4 will become 2 and 2 again. So 2, 2, 2. Eventually, we have how many? 6 2s. And 160 is 16 times 10. And this is a 4 times 4. This is a 2 times 5. Each 4 is 2, 2 multiplied together. So eventually we have 5 2s and 1 5. 224 is same process. I know at least that this can be divided by 2. So divided by 2, 22 divided by 2, 11, 4 divided by 2 is 2. This one can be divided by 2 again, divided by 2. 11 divided by 2 is 5. The remainder is 1. 12 divided by 2 is 6. 56 is 7 and 8. And 8 is 3 2s. So how many 2s we have? 5 2s for this one. And 1 7. And that's it. 5 2s and 1 7. Now, after that, we can write greatest common factor. First, look at the common factor first. They all have 2s. And among all of these exponents, pick the smallest. This is a 5. I mean, this is 5. This is 5. This is 6. 5 is the smallest. Then any other common factor? The answer is no, because this one, the first number doesn't have any factor other than 2. So no more common factors. So this equals 32. If you multiply 2 by itself 5 times, that's 32. That means all of these numbers can be divided by 32 evenly, and 32 is the largest part. Now let's look at the second method, box division. We're going to put these 3 numbers inside the box. Now we need to have common divisor to all of these 3. So at least 2, because they're all even numbers. This is going to be 32. This is 80. That's 1, 1, 2. So it can still be divided by 2. Divided by 2 is 16. This is 40. This is 56. Can still be divided by. If you say 8, that's perfect because you know they all can be divided by 8. Let's do 8 as long as it's common to all. Okay. 16 divided by 8, that's 2. 40 divided by 8, that's 5. 56 divided by 8, that's 7. Now among these 3, no common divisor anymore. So multiply them all together. So greatest common factor equals 2 times 2 times 8. 2 times 2 is 4. 4 times 8, 32. So you make decision which method you want to use. The result will be the same, right? Yeah. Now exercise number 4. Our next topic, find the greatest common factor of a set of monomials. That means we're going to have variables in it, not just numbers. But basic logic, basic mechanism is identical. So our first example, we want to find the greatest common factor of 18x to the fourth power and 12x to the third power. Now, we do this separately. We do number first. Between 18 and 12, these two numbers are small enough. You can see they all can be divided by 6. 6 is the largest number that can do that. So our numerical part of greatest common factor is 6. After that, we look at the variable part. We don't need to do any factoring, already done for us. So this is all multiplied together, right? We pick this for this same factor x. We just pick the lowest exponent. So that's x to the third power. And that's a final answer. So it's not difficult actually. Imagine x can be any number. If x is say 5, you have 3 5s in here, you have 4 5s in here. How many 5 is common? 3 5s, right? So this x could be any number. Doesn't matter. And let's look at more examples. This next one, greatest common factor. So between 24 and 40, if we do a quick box division to determine the greatest common factor between these two numbers, I see it can be divided by 4. It's going to be 6. This is going to be 10. It can be divided by another 2. This is 3. This is 5. So there's no common factor between these two. So that's 8. So the number part is 8. And the letter part is easiest, actually. Pick the smallest one for the same letter. So that's n squared. So greatest common factor for this one is 8 n squared. Now next one. And this one is interesting. 14. Apparently, we don't have a common factor in terms of letter because this one doesn't have any variable. So between 14 and 45, there's no common factor. If you want to factor it, this is 2 and 7. 45 is 5 and 9. 9 is 2 3s. So nothing is common here. So there's no common factor. The solution is 1. Only one can divide it into both. And one always a common factor. And the last one, we have 3 monomials. Let's look at the number part. Let's do a box division method. Box divisions can save you some room. 27, 54. I say all of the numbers can be divided by 3. So we learn divisibility rule, right? These 2 digits add together is 9, which can be divided by 3. Same thing here, same thing here. They're all divisible by 3. This is 6, this is 9, this is 18. They all can be divided by 3 again, looks like. So let's divide by 3. This is 2, this is 3, this is 6. Now, among these three numbers, 2, 6, 2, 3, 6, there's no common factor. Common has to be common to all of these numbers, not just between 2 and 6, for example. So normal common factor, this is our final answer, is 9. So for the number part of our greatest common factor is 9. Now let's look at the variable part. We have only y. The smallest exponent is 2, so y squared. So final answer, 9y squared is our greatest common factor. And this is your last exercise set. And this is also the end of the video. See you in the next one.